Hey everyone, welcome back to Explore Electronics. In this video, I am covering Module 2, that is Oscillators and Operational Amplifiers.
What is oscillator? The oscillator is a circuit which produces a continuous signal or repeated signal we can say, which is an alternating waveform also we can say. And also we can define oscillator as it is an essential device that produces periodic electronic signal, typically a sine wave or square wave generally. Or also some oscillators will produce sawtooth wave like this, triangular wave and a rectangular wave also. So here feedback is very important concept in designing of oscillators. We know feedback is providing a fraction of the output signal back to the input of the amplifier, that is feedback. There are two kinds of feedback. One is positive feedback, another one is negative feedback. Positive feedback is that the input signal and the feedback signal coming to the input are in phase. This is positive feedback. If the input signal and the feedback output are not in phase, means out of phase, that is negative feedback. This positive feedback is used in oscillator design. Negative feedback is generally used in amplifier design. So this is the positive feedback circuit. In positive feedback, we are going to get the same phase with respect to the input signal as well as the feedback network output. These two are in phase. Now we need to derive the expression for overall gain of the circuit so that we will be understanding how actually the gain is going to be varied. The overall gain of this circuit will be taken as V out divided by V input, that is represented as G. By applying KVL to the input side, it is V in dash. V in dash is the signal coming into the amplifier after the feedback network is given. So V in dash is equal to V in plus beta into V out. Here why we are doing plus means, why we are adding these two means, since it is a positive feedback, the input signal as well as the feedback signal are going to be added up here. That's why V in dash will be generated by using V in signal plus beta into V out. This is the feedback signal. If we rearrange this expression, V in is equal to V in dash minus beta times V out. And we know that the only amplifier we have here without a feedback network, the gain of the amplifier will be AV, and it is V out divided by V in, the input coming to the amplifier. So in this expression we can write V out as AV into V in dash by using this expression. Now we got the expression for V in as well as V out, so we can take the overall gain G by using the two expressions, equation 2 and equation 3. If we substitute, G becomes AV into V in dash, this is for V out, and V in dash minus beta into V out we can write over here. In the denominator we have V out again. We can use this expression again in place of V out, AV into V in dash. So by looking at this expression, in the numerator also we will be having V in dash, and in the denominator we can take V in dash as common here. So if we take V in dash as common and V in dash get cancelled, the remaining expression is AV divided by 1 minus beta into AV. So oscillator output may be of any of these kinds. Okay, it can be a sine wave varying like this, or it may be something like a continuous signal like this. So we need to understand, to get the continuous signal with sustained oscillation in the sense without any such disturbance, we should get a sustained oscillation. The oscillator should be satisfying some conditions. So let us see what are all the conditions the oscillator should satisfy to get a sustained oscillation. So one thing we understood is that in the oscillator we should have a positive feedback. That is what the first condition is. The feedback must be positive. We should have a positive feedback with an amplifier to get the oscillation. So the signal feedback must arrive back to the signal and both are in phase. That is what we say a positive feedback is. In other words, we can say a phase shift of the amplifier, okay, and the feedback network should be 0 degree or 360 degree. then only we say it is a positive feedback. That is the first condition. The overall phase shift should be 0 degree or 360 degree. And the second condition is that the overall loop voltage gain, means the overall gain G, must be equal to 1. We need to design the amplifier and the feedback network in such a way that the overall gain should be equal to 1. Means A is the gain of the amplifier, beta is the gain of the feedback network or the feedback factor. If we take the product of those two, that should be equal to 1. These two are the conditions a circuit should satisfy to get the sustained oscillation as the output. What happens if A into beta is greater than 1? If A into beta is greater than 1, we are going to get a growing type oscillations. It is not the sustained one. And the oscillations are going to be growing up. The voltage is continuously increasing. If A into beta is less than 1, what happens? The voltage of the signal we are getting is going to degrade. It will be called as decaying type. If A and beta is equal to 1, then only we are going to get a continuous signal like this. This will be called as sustained oscillation. So let us understand the different types of oscillators. In that, first one is ladder network oscillator, or it will be also called as RC phase shift oscillator. You can observe here we will be having a combination of R and C, right? The three combinations of R and C will be act as a feedback network, a positive feedback network, and the rest of the circuit here with a BJT will be an amplifier circuit. Okay, so TR1 is a common emitter amplifier circuit here by using a BJT, and R1 and R2 providing base potential, and we are using a base bias here to bias this transistor to operate as an amplifier, and R3C1 providing emitter stabilization. Okay, this is what the amplifier is, and the three combination of R and C will be a feedback network. Here we need to understand the RC ladder network combination of R and C, three pairs are producing a 180 degree phase shift. That will be act as a positive feedback, and it is producing 180 degree phase shift. And another 180 degree phase shift will be getting from the transistor, means the amplifier. So in the previous slide we have seen we need to have the oscillator condition in such a way that the overall gain of the circuit should be 360 degree. So after connecting a positive feedback, here that positive feedback is generating 180 degree phase shift and the amplifier is producing 180 degree phase shift. That's why the condition satisfies the overall phase shift will be 360 degree. And frequency of oscillation from this circuit is F is equal to 1 divided by 2 pi into root 6 into CR. This is the expression for the frequency of the signal we are going to get. So to understand that how actually we are going to get a 180 degree phase shift from the RC network, we need to go for this circuit. Here one pair of RC network is shown. Here the capacitor reactance is XC. This XC can be written as 1 divided by omega C. Here omega is the angular frequency and C is the capacitance. So the phase shift provided by this particular circuit is tan inverse of XC divided by R. So depending on the value of the resistance and the capacitance, here we are going to get the phase shift. So if you look at this expression tan inverse of XC by R, if the value of XC is very small, means XC becomes 0, the numerator becomes 0, what happens? The phase shift will be 0. If R becomes 0, the denominator is 0, let us assume R is 0, we are going to get 90 degree as phase shift. Means from this circuit we can expect the phase shift from 0 degree to 90 degree. A single RC network is going to provide maximum of 90 degree phase shift. But if we use two such combination of RC networks, we can expect a 180 degree phase shift. But the maximum phase shift we can expect is 90 from one pair. It is difficult to get the total phase shift of 180 degree if you use two such pairs. That's why three such pairs are going to be used. Here you can observe These three pairs are going to provide 60 degree, 60 degree, 60 degree. The total phase shift will be 180 degree. Or the RC network is going to be designed to provide 45 plus 45 plus the remaining like that, so that the overall phase shift should be 180 degree. This is how the RC network is going to provide a phase shift. And after providing the 180 degree phase shift from the feedback network, another 180 degree provided by the amplifier. So we are going to get a sustained oscillation like this. This is the another way of writing the same circuit. Here you can observe up to here we are going to get a 60 degree phase shift, and the second stage is going to give the another 60 degree. The third stage is going to give another 60 degree. The total phase shift of this network will be 180 degree. Another 180 degree will be provided by the amplifier. So the frequency of oscillation will be written as 1 divided by 2 pi into root 6 into CR. Since we have 3 stages here, this is root 6. This is actually generally it is 2 into n. If the number of stage is 3, this n is 3, that's why it is root 6. If 2 stage is there, it is root 4. The another kind of oscillator is Wien bridge oscillator. In the Wien bridge oscillator, you can see the figure here. The circuit of RC network is connected in a bridge fashion. Okay. Here we are going to apply the input signal to terminal A and B, and output is taken from C and D. Okay. Here at one particular frequency, here in the previous oscillator we have seen the frequency expression, that is the resonant frequency of the oscillator. Means the oscillator is going to provide the oscillations with that particular frequency. Similarly, here also in the Wien bridge oscillator, at one particular frequency in this bridge network, we are going to get the phase shift of the signal exactly 0. So the condition of the oscillator is that the overall phase shift of the should be 0 or 360 degree. So this Wien bridge circuit will be act as a positive feedback network. This positive feedback network is going to give a phase shift of 0 degree at particular frequency. That particular frequency is the resonant frequency. And if the feedback network is giving 0 degree, obviously an amplifier also should give a 0 degree phase shift. We should have an amplifier which is producing 0 degree phase shift, and this will be act as a positive feedback, and at particular frequency this circuit will give 0 degree phase shift. That satisfies the condition of oscillator. So now let us understand how actually we are going to get that phase shift and what actually the gain should be. The minimum amplifier gain required to sustain oscillation is this. It should the gain of the amplifier should be equal to 1 plus C1 divided by C2 plus R2 divided by R1. Here if we take C1 is equal to C2 and R2 is equal to R1, the gain of the amplifier becomes 3. So this is the gain of the amplifier by taking C1, C2 and R2 and R1 into account, right? And the frequency at which the phase shift will be 0 is this. The expression for resonant frequency F is 1 divided by 2 pi into under the root C1, C2, R1, R2. Since C1, C2, R1, R2 are equal, if we take equal, the expression becomes 1 divided by 2 pi into root of C square, R square. So if we take root and square cancel, it becomes 1 divided by 2 pi into CR. So this is the expression we are going to get for the frequency. This frequency signal is going to be generated when AV is 3 and beta if we are going to adjust it to 1 by 3. This satisfies the condition of oscillator. This is how the Wien bridge oscillator is going to produce oscillation when R1, R2 are equal to R and C1, C2 equal to C. Here also you can observe the first half of the circuit is a bridge network. It will be act as a positive feedback, and the rest of the circuit is the non-inverting amplifier circuit. Okay, this is a non-inverting op-amp amplifier. So non-inverting amplifier producing 0 degree phase shift. Here also this particular positive feedback Wien bridge network producing 0 degree phase shift. That's why this will be an oscillator, this producing oscillations with this particular frequency. And you can rewrite the circuit like this. You can easily understand here. This is a an op amp which is connected in non-inverting fashion. So this is the input signal and inverting terminal is grounded. This will be act as non-inverting amplifier which produces 0 degree phase shift. And second half of the circuit is the Wien bridge oscillator. This produces again 0 degree phase shift, so that we are going to get a sustained oscillation out of this circuit. Now let us go to the next topic, that is single stage astable oscillator. It is astable oscillator. Astable oscillator in the sense, in the previous topic we say astable means it will produce a continuous square wave. Now let us understand how this circuit works. So it is an op amp, an amplifier circuit, and with an amplifier circuit we should have a positive feedback. So this is the positive feedback circuit which is connected to a positive terminal of the op amp. So this will be act as a feedback network and this will be act as an amplifier. Here in the single stage astable oscillator we will be having one capacitor here. So this capacitor is the heart of the circuit here. When this capacitor charges, the value will be raised to 1, and it discharges, it will be coming back to 0. Like that, the output of a pulse will be generated in a astable oscillator here. Now let us assume this C is initially uncharged. Uncharged in the sense the value at the capacitor will be 0. It is not at all having any charge. So at this stage, voltage at the inverting input terminal, here it is less than the voltage at the non-inverting input terminal. Why? Because there will be an offset voltage here at the output of the op amp, since there is no voltage at the input terminal. By considering that, if we compare the voltages at the inverting and non-inverting terminal, let us treat non-inverting terminal is greater compared to the voltage at the inverting terminal, since this capacitor will be having 0 volts. In this case, what happens? Because of the voltage available at the non-inverting terminal, output will be a non-inverted output, means output will be raised to plus VCC, right? And this value will be stayed for some time. Because of Vout is high, this path you can observe here, through R there will be current flow to the capacitor. This high voltage at the output, this will make a current flow through this resistor, the negative terminal resistor R, and this capacitor will be charged. Once this capacitor will be charged, what happens? The terminal voltage in the negative terminal, or we say the inverting terminal voltage, is greater than the non-inverting terminal now, because of this capacitor charged like this, plus minus. So because of this plus terminal of the capacitor here, this voltage is more compared to the non-inverting terminal voltage. Because of the inverting terminal voltage, the output of the circuit reduces to minus VCC, and this voltage will be stayed for some time. This capacitor will be started discharging now. Once the capacitor becomes discharged, the voltage at the inverting terminal is coming to 0, or we say minus VCC. Now if we compare, the output is also minus VCC, and it will take a path to discharge, and the output voltage, or the voltage divider output, which is available at the non-inverting terminal, is greater compared to the inverting terminal now. Why? Because capacitor is discharged. That's why, as compared to the inverting terminal, non-inverting terminal will be having more potential. Again, voltage rises to plus VCC. This process continues. Again, capacitor will charge when the output voltage is maximum. Then capacitor will discharge in the negative output. Again, it will be charged and discharged. This is how the output of the astable oscillator is going to be obtained as a continuous train of pulses. And if you write the upper cutoff as well as the lower cutoff, or we say upper threshold or the lower threshold voltage available at the input of this op amp, this is VCC into R2 divided by R1 plus R2, and the lower threshold is minus VCC into R2 divided by R1 plus R2. Or if you apply a voltage divider rule over here by considering this Vout as plus VCC and minus VCC, we are going to get these two expressions. And the time period means from here to here. What is the time taken by the oscillator to get one complete cycle means this is T. 2CR natural log of 1 plus 2 into R2 by R1. This is what the time period of the signal, what we are going to get as output. And then we have crystal oscillator. Crystal oscillator is again a kind of oscillator where we are going to use a crystal within the device. In a oscillator circuit, we will be having a crystal. Here in the circuit you can observe this X1 is a crystal. Here they have considered it as a quartz crystal. This quartz crystal, what happens, it is going to vibrate when the potential difference is applied. When we are going to apply the voltage across the crystal, the crystal is going to vibrate. This crystal can be related to the electrical quantity as a RLC circuit. And when this crystal vibrates, that phenomenon will be called as piezoelectric effect. Because of the potential difference, the crystal vibrates. Here the kind of crystal we are going to use is quartz crystal, and that effect is piezoelectric effect. So the frequency of oscillation, the output will be a continuous wave here. The frequency of oscillation is depending on the size of the crystal as well as the cut of the crystal. Cut in the sense we are going to take the crystal wafer, and the wafer cut will be taken to manufacture this crystal or to make this crystal. That will be called as crystal cut, and the physical size will be representing the frequency will be depending on those two. And these crystals are the crystal oscillator which will be connected in a positive feedback manner, and this transistor will be making the amplifier circuit. Here it is again giving an continuous oscillation. What is the amount of frequency we can get from these crystal oscillators means, if it is operating in a fundamental mode, the output will be from 100 kilohertz to 20 megahertz, means the high frequency generations can be made using these crystal oscillators. And if it is operating in a overtone mode or overtone operation, we can expect an output of 20 megahertz signal or 100 megahertz signal from the output of these crystal oscillators. You can observe this is the practical crystal oscillator device we are going to get practically. So on this it is mentioned it is going to give 4.0000 megahertz of frequency. This is what crystal oscillator is. In this video I am going to explain about op amp parameters, op amp characteristics, op amp configurations, different circuits using op amp like inverting amplifier, non-inverting amplifier, integrator, differentiator, voltage follower, like that. First we need to understand what is op amp. Op amp is an operational amplifier. It gives high gain with a differential input and single-ended output. There are two input terminals here we can observe, and only one output terminal in the diagram we can see, and two power supplies. Out of two input terminals, one is inverting input terminal and another one is non-inverting input terminal. Those are represented with negative and positive sign. So we can apply the two voltages here and we can expect a difference between the two, and that is amplified as output. So basically this op amp will be called as a difference amplifier. And the two power supply connections you can see here. From here and here we have to provide plus means positive supply as well as negative supply. So for the positive supply, here you can observe a positive rail supply, the series of batteries connected, and the positive end will be connected over here and the negative end will be connected over here. A balanced power supply we need to provide, means if we provide a plus 5 volts here, we need to provide minus 5 volts as a negative supply. Similarly plus 7, minus 7, something like that. we need to give as a power supply to the op-amp. Now let us see the different parameters of op-amp. Since this is an amplifier, we need to concentrate on gain of the amplifier. So first one is op-amp open loop voltage gain. The open loop voltage gain of an op-amp is defined as you know, ratio of output voltage to the input voltage. Since it is a open loop gain, we should not have any feedback. That's why no feedback applied is the thing here while taking open loop gain of a amplifier. Obviously, we have seen in the previous videos also while explaining the amplifier, I said gain in the sense it is output divided by input. If it is an voltage gain, we need to take V out divided by V in. If it is a power gain, we need to take power output divided by power input. Similarly, current gain, current output divided by current input. When we say open loop voltage gain, there is no feedback applied in the circuit. And open loop voltage gain will be represented in decibels. Generally, gain will be represented in decibels. So, if we convert that voltage gain into decibels, it becomes we need to take 20 log of that ratio. If it is power gain, we need to take 10 log of that ratio. So, most of the op-amps will be having an voltage gain when it is in the open loop condition of 90 dB or more. So, we will see closed loop voltage gain. Closed loop voltage gain in the sense when the feedback is applied, when there is a feedback signal applied. The closed loop closed loop voltage gain of an op-amp is defined as again the ratio of output voltage to the input voltage with a small proportion of the output voltage fed as an input, that is called as feedback. So you can observe here, we are going to get a large voltage gain. If the voltage gain is unity, the bandwidth will be around 1 megahertz. As we get the more voltage gain, generally the voltage gain in closed loop circuit will be in several thousands. But as we get the more voltage gain, if we are expecting a more voltage gain, we need to compromise with the bandwidth of the circuit. You can observe as gain increases here, the bandwidth reduces. Okay, the different frequency signals op-amp can amplify going to be reduced as the voltage gain increases, right? And then input resistance. This is also as we seen in the amplifiers video. Rin is the input resistance, that is voltage input divided by current input. Practical value of this input resistance will be 2 mega ohm for a common bipolar type of op-amp, and it go up to 10 power 12 ohm. Means remember, for an amplifier we should have high input resistance. Input impedance of the amplifier should be high. So here also the input impedance is high in op-amp. And then output impedance should be less, right? Output impedance or the output resistance should be less. Here V out divided by I out gives the resistance at the output. And the typical value of the output resistance will be from less than 10 ohm to around 100 ohms. You can compare here the typical values of input resistance as well as the output resistance. Input resistance is in mega ohms or 10 powers, but the output resistance is 10 ohm up to 100 ohm it can go. And one more concept here, it is input offset voltage. The ideal op-amp, if we consider an ideal op-amp, the output of that ideal op-amp should be 0 when the difference is applied to its input. Means the output should be 0 when there is no input. Okay, if it is not giving 0, if the small voltage is getting as an output, we say there is no balance, there is an internal imbalance in the circuit. To make that output 0, we need to adjust the offset voltage. We need to provide an extra input so that op-amp output will be 0. So that voltage will be known as an input offset voltage, and typically it will be in the range of 1 millivolts to 15 millivolts. Remember, this is an voltage applied to an op amp to make the voltage exactly 0. Okay. Then full power bandwidth. As you know, bandwidth in the sense the range of frequencies an amplifier can amplify. That is bandwidth. A lower frequency to upper frequency of signals an op amp can amplify is called as full power bandwidth without any distortion. A full power bandwidth of an op amp is equivalent to the frequency at which maximum undistorted peak output voltage swing falls to 0.707. This is what I explained in the previous video, that is 3 dB less, right? We take 3 dB lower in the frequency response, that is in the DC value it is 0.707 times the maximum value gain, right? So typically the full power bandwidths range from 10 kilohertz to 1 megahertz, means the maximum bandwidth the op amp can take is 1 megahertz from high speed devices. Then slew rate. What do you mean by slew rate? Slew rate is the rate of change of output with respect to time, right? Means where delta V out is the change in the output voltage with respect to time, means when there is a small change. So that amount of value will be called as a slew rate. So slew rate is measured as volts per second, or we take volts per millisecond or microsecond also. This value range from 0.2 volts per microsecond over 20 volts per microsecond. And then op amp characteristics. Here we need to understand when the op amp is in ideal condition and when we are using the op amp in a practical condition. Ideally, you can observe here in the table, the voltage gain is infinite. Voltage gain of the op amp should be infinite. In practical times also it is a higher value. And input resistance. We know that input resistance in ideal case should be infinite. Here also in op amp it is infinite. When we take the practical value it is 100 mega ohm. Then output resistance. Output resistance should be 0. In ideal case it is 0 and it is very less value in real time. And bandwidth of the op amp should be infinite. In ideal case it go up to 1 megahertz or 2 megahertz practically. And slew rate should be maximum or infinite, we say. It is 10 volts per microsecond. And input offset means the offset voltage a op amp should take should be 0. There should not be any input offset voltage it should take to make the output as 0. And obviously in the practical case it is a minimum value, it is less than 5 millivolts. The same explanation given here, the open loop voltage gain should be very high, the input resistance should be very high, output resistance should be very low, and bandwidth should be maximum or wide as possible, slew rate as large as possible, and then input offset should be less. And this is what the different op amp ICs available. Here you can observe the type, and it is bipolar type, FET type, CMOS type, FET, bipolar with different open loop voltage gains. You can observe here, this is what the different voltage gains for these different ICs available for an op amp. Generally the famous one or the typical one we are going to consider always is 741. This is a general purpose op amp. These are the different kind of op amps available. You can observe the voltage gains with respect to these devices and input bias current, slew rate, and the amplification type. And then op amp configurations. This is what very important concept here is. The three op amp configurations we need to discuss here importantly. One is inverting amplifier, another one is non-inverting amplifier, and then differential amplifier. Now let us see one by one. First one is op amp inverting amplifier. So as I said, there are two input terminals. One is negative, another one is positive. Means one is the inverting input terminal. This is inverting input terminal. This is non-inverting input terminal. So when we apply the voltage to an inverting input terminal, when we are applying the voltage to the inverting input terminal by grounding the non-inverting input terminal. You can observe here, it becomes an inverting amplifier. Remember, we are applying the voltage to the inverting terminal and non-inverting terminal is grounded. So this Rn is an input resistance here for the voltage what we are going to apply, limiting resistance, and Rf is the feedback resistance. Here we have used a feedback through Rf, which is connecting to the inverting terminal of the op-amp. Always the feedback will be for the inverting terminal, so that we can say this is an negative feedback. Negative feedback in the sense, in the amplifier circuits we are going to use negative feedback, which we have discussed in the previous video. So once we apply the voltage to the inverting terminal, obviously output will be taking 180-degree phase shift. Here you can observe this is an input signal and output signal will be taking 180-degree phase shifted output. So exactly the inverted output we are going to get. So the output V out can be written as minus Rf divided by Rin into Vin. Here this is the gain. Okay, Rf divided by Rin is the gain. So gain is in minus or negative. So we say the inverting amplifier is going to amplify the signal, but output will take 180-degree phase shift and the gain will be negative. Next we have non-inverting amplifier. In non-inverting amplifier the arrangement will be same, but we are going to apply the input from non-inverting terminal and inverting terminal is grounded here. So now when we apply the input to the non-inverting terminal, what happens? The output should not be taking a phase shift. It will amplify, but the phase shift should be 0. Why? Because we are applying for the non-inverting terminal. And V out, if you observe the output, it is 1 plus Rf divided by Rin or R1 into Vin. This is what the gain here. The amount of gain we are going to get is 1 plus Rf divided by R1, and here you can observe the gain is positive. Since it is a non-inverting amplifier, it is not inverting the output, it is amplifying with a gain of 1 plus Rf divided by R1. Then we have difference amplifier. We can use op-amp to subtract the two input signals. Here is the arrangement for that. Rin and Rin are the two input resistances we are going to connect. Let us take this as V1 voltage, and here we are going to provide V2 voltage. Okay, and this is the feedback network and Rf is the feedback resistance. The same kind of resistance we are going to use here. The value of Rf is same here also and Rin is same, and we are going to provide two voltages V1 and V2. This circuit will give the output as V out is equal to Rf divided by Rin into V2 minus V1. So if Rf and Rin are equal, here these two resistances are equal and these two are equal. Suppose if we use Rf as well as Rin same, what happens? These two get cancelled and exactly V out will be V2 minus V1, right? This will be act as a perfect subtractor now if we take all the resistances equal. You can observe here V1 and V2 signals. This is V input 1, it is more than V2. So the output is V2 minus V1. So V2 minus V1 is the negative value, so that we are going to get a negative value here. And this signal is an output. The two dotted signals are two inputs. And one more thing is that the bandwidth of the amplifier, if the bandwidth of the amplifier is exceeds that of the input signal that is required to amplify, what we should do? We need to restrict that, right? We need to limit the band. In such cases, we are going to use capacitor such as CF and Cin, which is included with the inverting amplifier. Okay, if the capacitors with an appropriate value is used, inserted in series with Rin as well as parallel with Rf, here we can reduce the bandwidth. So F1 can be calculated using this expression, 1 divided by 2 pi Cin into Rin. and F2 is again 1 divided by 2 pi CF RF. So the two frequencies we are going to get, and we can write the frequency response like this by taking an 3 dB lower or 0.707 times the gain. Here is F1 as well as F2. Okay. And one more configuration of op-amp, that is voltage follower. Voltage follower is, as the name itself indicates, the output is going to follow the input. There is no feedback resistance here. Feedback resistance is 0, and we have no limiting resistance connected at the inverting terminal. We can treat that as infinite. So if we apply this concept of RF is equal to 0 and Rin is equal to infinite to an inverting terminal, inverting amplifier Vout expression, we are going to get Vout is equal to Vin. Okay. Take RF is equal to 0. Since there is no feedback path here, we can treat this RF as 0. By taking this RF 0 and Rin, or the resistance over here, is infinite, we are going to get Vout is equal to Vin if we apply to the inverting amplifier. Then the waveform, if you observe, this is Vin, the signal, and output will be same. The output is following the input. And op-amp can also be used as differentiator. The signal differentiation we can take by applying an input from the inverting terminal by using a capacitor here. In the feedback path, we are going to use a resistor. This differentiator produces a output voltage that is equivalent to rate of change of its input. That is what the meaning of differential output is. So let us take an example of square wave input which we have given. Here the square wave input is converted into a short duration pulses. Okay, when there is an change in the input, rate of change of input, it gives a output. When there is a change in 0 to some negative volt, here you can observe we are going to get some positive peak value. Since it is an inverting case, we are applying an input to the again inverting terminal, obviously output will be phase shifted 180 degree one. So this circuit differentiator is producing pulses like this when there is a change in the value. You can observe here when there is no change in the value over here, the output will be 0. When there is a change from 0 to 1, again a peak will come, right? This is how the differentiator will give the output. Similarly, we have integrator also. The integration of the input we can take. The integrator output will be a ramp wave. It can also be called as a ramp generator. Okay. When there is an input going from 0 to 1, when there is an input going from 0 to 1, here also the output will be changing as a ramp wave. Okay, it is increasing, again decreasing, again increasing, like this as the input voltage changes its value. Then we have comparator. So if you look at the circuit, the two voltages V1 and V2 are given, and we are expecting this to be act as a comparator. Means it should give the output by comparing the two inputs, whether it is high, V1 is high or low, V2 is higher or lower, like that. So you can observe the waveform. By looking at the waveform, we can understand this circuit. This is input voltage V1, means this is a constant value. So let us take this as a voltage we are going to give as a constant voltage like DC volt of 5 volts. And here is V2, V2 is varying one we are giving just for the comparison of these two. And we are going to get the output to the maximum value when this V2 is higher than V1. When V2 is less than V1, we are going to get the lowest value. Means since there is no feedback is connected here, the output of op-amp will be maximum, right? Maximum in the sense to the power supply voltage what we are going to give, up to that the voltage is going to be raised. So here output is going to be produced by the op-amp will rise to the maximum possible value when voltage present at non-inverting terminal exceeds the present at the inverting input terminal. Means V2, as V2 is higher than V1, when V2 is more than V1, you can observe here in the dotted line, it will reaches the maximum value. Vout will be maximum. Means suppose if we give a positive 7 volts from here as a power supply, it will reaches 7 volts irrespective of the V1 and V2, right? It reaches the maximum value. Similarly, the balanced power supply means from here we are going to provide minus 7 volts. If it is minus 7 volts, when V2 is less than V1, it will reaches minus 7 over here. This is how we can use op-amp as a comparator. And op-amp summer, it will be also called as weighted summer, or we can generally call it as adder. We can use the op-amp circuit to add two voltages. Here if we apply V1, voltage 1, and this is voltage 2 to the inverting input terminal of the op-amp, and non-inverting terminal is grounded, here it is grounded, and this is an feedback resistance, we can expect the output will be the addition of these two, V1 and V2, with the weights RF and R1, R2 if we take. If we take all the three resistances are same, the output will be like this. Vout is equal to minus V1 plus V2. Why it is minus means it is the inputs are connected to the inverting terminal of the op-amp. That's why it is minus V1 plus V2.